and I'm going to share my screen. And I'm going to look in OneNote for today. And today we're going to be looking at the division of polynomials. We're also going to be looking at the introduction to factoring. Homework P3 is due by the end of today. That's on radicals and also on those rational expressions. Homework P4 is due by Wednesday. That's under operations of polynomials. So far, we've added, subtracted, and multiplied polynomials. Today, we're going to look at division, and that operation of division on polynomials is going to lead us to that idea of factoring. P5 is due on the 17th, which seems really, really way off because that's more than a week away, except realize that the 15th is a holiday. And so it's not that far off. We'll probably spend a couple of days factoring. Before we get started, does anybody want to look at anything in my labs, any homework questions?
Could you go back to your first notes there so I can?
Yeah, I will eventually go back there. I was trying to open the homework, and what happens is the Zoom toolbar gets in the way. Does anybody want to look at anything at all from my labs, any homework questions?
I'm not able to pull mine up right now, but I remember the problem.
Sure, you can just tell me it.
It was a square root over 2 over square root of 11. Or just root.
Sorry about that, folks. So it was the square root of 2 over the square root of 11. And you can't leave a radical in the denominator, and you can't leave a fraction under the radical. We could change that into the square root of 2 over 11, but that fraction doesn't simplify. So going that route doesn't help us. To get the radical out of the denominator, we do that process that's called rationalizing the denominator. Because there's only a single term in the denominator, a single radical in the denominator, we're going to multiply the denominator by that. But because we don't want to change what the fraction's equal to, we have to do the same thing to the numerator and the denominator. This gives me the square root of 22 over with the square root of 11 times the square root of 11 would be the square root of 21, which is, 121, which is just 11. When we multiply a radical by itself, no matter what it is, when I take a square root and multiply it by itself, I'm always going to just get the radicand. Sometimes we end up taking that absolute value. Better?
Yes.
You remember doing that in class?
Yeah, I messed up because I multiplied by 2. I don't know why. I thought it'd be easier, but.
Yeah, and that last quiz, there were a few people who did that. But no, it's okay to have a radical in the top. It's not okay to have a radical in the denominator. Kind of got to get the skeletons out of the closet, clean out the basement or whatever. We can't leave a radical in the denominator. So you're always multiplying by what's in the denominator. Okay?
So then the answer to that is the square root of 22 over 121 or 11?
Over 11. Because over here, where I took radical 11 times radical 11, it is radical 121, which is just 11.
Okay.
Okay. Does anybody want to look at anything else from any of the past homeworks?
How'd you get 11? Like, why did the square root of 11 turn into just 11?
Because when I take the square root of 11 and multiply it by the square root of 11, technically 11 times 11 is 121, and its square root is 11. Or in general, when I take the square root of something and multiply it by itself, when I take the square root of that quantity squared, it always just gives me what's under the radical. So if I had the square root of square root of 5 times the square root of 5, that would give me the square root of 25, which is just 5. If I had a square root of 72 times the square root of 72, it turns out to just be 72. When I multiply a radical by itself, because I end up taking the square root of that quantity squared, they kind of undo each other. And so it just gives me the radicand. Only with the square root. Other roots, you'd have to do more. Any better?
Yeah.
Okay. Any other questions? I have to apologize. I got through most of the quizzes that I had received before the Super Bowl started, but I did not do any grading after the Super Bowl started because I had, and for a whole bunch of reasons. I did do a few more this morning. I got through, I think, most of the quizzes, but not all of them. If you did not email me your work, yours isn't graded. You need to email me your work. If you did not email me a picture of the work that you did to support your quiz, you must do so. Does anybody want to look at any of the quiz questions before we carry on?
I have a question. So my free trial expired, and I got in an accident. My car got totaled, so I don't have a car right now. So I have to get up to the school to buy it.
Until, and I was talking to somebody else before class, if your free trial ran out, send me an email. What I can do is send you worksheets that are equivalent to the homework, and you can do those worksheets, but you have to return them to me by the whatever the due date is. And I only grade them once, but if you need to, you can do it that way. I'm just appreciate that you did make use of that free trial, because that put your name in the MyLabs grade book, so I have a place to record the grades when you turn in those homeworks, okay?
All right.
But please send me an email reminding me if you do need those pencil and paper copies, okay?
All right, I will.
And are you all right after the accident?
Yeah, I mean, this was a couple months ago.
Okay.
I was a brand new car, so I didn't really get
Ouch.
anything. Yeah.
Ouch, 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 not good. So, okay, let's see. Anybody want to look at anything else?
Yeah, the number 7 on the quiz had me completely lost.
Can you and the quiz was set up so that the questions were the same for everybody, but they weren't necessarily in the same order. Can you remember what the quiz question was?
Yeah, it was 5, and then the square root of 180 plus 6 and the square root of 20.
Oh, you guys, the battery is running out on my stylus and it's not working. So give me just a minute. I have this replacement stylus somewhere, but somewhere is a keyword there. So I am hoping, does anybody, when a battery starts going, get desperate and like take it out and rub it on something and hope that that works? So you have this, say that again.
It was 5 and then the square root of 180. 6, the square root of 20.
And you were adding them. And right now we can't add them because they're not the same. And so what we need to do is try to simplify them. So if I look at 180, 180 is divisible by 10, but 18 isn't a perfect square. It's divisible by 5, and I get 36. 36 is a perfect square. So I'm going to simplify that. So that'll give me 5 times the square root of 36 times the square root of 5. So that'll give me 5 times 6 times the square root of 5, or 30 square roots of 5. With me so far?
Where did you get the 5 from?
This 5?
Yes.
I just have to say what numbers multiply to 180 and one of them's a perfect square. And I'm looking for the biggest one. And so because I got multiplication facts drilled into me when I was a little kid, I recognize that that's 36 times 5. If you
Okay.
didn't see the 36 and the 5, you might have gone, well, that's 9 times 20. 9's a perfect square. We could do that. We take the square root of 9 times the square root of 20, which gives me 3 square roots of 20. But 20 can still be broken down, right? What number goes into 20 that's a square? 4. And so that would give me 3 times the square root of 4 times the square root of 5. Or 3 times 2 times the square root of 5, or 6 square roots of 5. And notice that takes me to exactly the same place. It's just more work if you divide out smaller numbers to begin with.
So then the answer was 30 to the square root of 5.
No, that's not the full answer. That's just what this first part is equal to.
Okay.
Now we have to add that second part. So let's see, 20. What number goes into 20? That's a perfect square. 4. So that'll be 6 times the square root of 4 times the square root of 5. What's the square root of 4?
2.
2. And so that's 12 square roots of 5. And after all that work, originally I could not add them because they were different. But now that they're simplified, you see I can add them because they're the same. So adding 30 plus 12 is 42 square roots of 5. And so this is your final answer.
Okay.
Okay? So when you're adding them, in order to add them, your radicals have to be the same. If they're not the same, try to simplify them. And oh, you know what? I just had a crazy thought. I'm going to redo that problem. We have 5 square roots of 180 plus 6 square roots of 20, right? 20 is easier to break down, isn't it? Can you see that 20 is 4 times 5?
Yeah.
That one's easier to simplify, isn't it? And this is kind of sort of a cheater's way of doing it. Now that I got the 12 square roots of 5, I'm going to say, wait a minute, 5 go into 180. Yes, 36 times. And so if you simplify the easier one first, it gives you an idea as to what number you might want to try going into the harder one. Does that make sense?
Yes.
And so if you simplify the one that looks easier to simplify first, it gives you an idea as to what factor you want to use for the larger number. Okay? Doesn't always work that way. And if it doesn't work that way, you're not going to be able to add the birds anyways. So, okay?
Thank you.
You're welcome. Anybody else?
Can you do one more from the quiz?
Yes, but you have to tell me the question.
I'll look it up. Give me just a second.
Okay.
It's 3 over square root of 7 plus square root of 3.
I like that because this was one that a lot of people were not successful with. Based on what we just said, I cannot add those because they're different. And so, do you remember we said if there were 2 terms, we had to find the conjugate.
Yeah.
And for the conjugate, the 2 terms are going to be the same, but the operation in the middle is going to be the opposite. So the conjugate is going to be the square root of 7 minus the square root of 3. Now what I want to do with that is multiply both the denominator and the numerator by that. We have to do the same thing to both, and this should always be the same values but opposite operation. When I do that multiplication, in the numerator, I think everybody can see the need to distribute. I get 3 square roots of 7 minus 3 square roots of 3. Now, in the denominator, to multiply those, we could FOIL. Radical 7 times radical 7 is radical 49, which is 7. Radical 7 times minus radical 3 is minus radical 21. Radical 3 times radical 7 is plus radical 21. Radical 3 times negative radical 3 is negative radical 9, or minus 3. The middle guys will always cancel out. And so instead, we could kind of just cut to the chase and say that it's the first one squared minus the second one squared. And so that gives me 3 radical 7 minus 3 radical 3 over 4.
Is that the final answer?
That's the final answer.
Oh, okay. Yeah, the whole question got me so confused, the quiz.
Whenever you see those two terms in the denominator of the fraction, whenever I see those two terms in the denominator of the fraction, not gonna lie, before I even read the words, a big flashing neon sign goes off in my brain that says, oh my God, 2 radicals, I've got to use the conjugate. Okay,
Yeah, thank you.
you're welcome. Thank you for asking. So, in terms of going over things, we will start factoring today. We're going to factor for a couple of days. Those of you who took the introductory algebra 1 and 2 before this spent about a month factoring. We're going to do that month's worth of factoring in 2 classes. We're going to go on the assumption that everybody's done some factoring before, and we're just trying to brush up the cobwebs. But the practice that we do, factoring is one of those things where the more you do it, the better you are. And so there's an extra in Blackboard and learning modules content. And my internet's too slow today. Sorry, guys. And handouts. I put a present there for you guys. And the present is a factoring practice worksheet. I also took the liberty of adding that factoring practice worksheet to today's notes. And look at that. Isn't that a thing of beauty? It is 90 factoring problems. Not quite 100. There's 90 of them. I'm not going to require you do them, but I am going to say the more you factor, the more you practice, the better you are. And for everything you do from this point on, and those of you who are going to advanced algebra and trig, pre-calculus, calculus, and beyond, it's something that you're supposed to be able to do with ease. So the more practice, the better. And then, woohoo, second page are the answers. So you can practice and check yourself. Also, if you're one of those people who are having a little bit of a hard time right now with the multiplication and the foiling, you could look at this worksheet another way. You could look at this back and say, oh, they're all multiplication problems. And here are the answers. And so it's twice as much fun. You can use it to practice multiplying, or you can use it, as you'll see later today, to practice factoring. So just want to make sure that everybody's aware that that's there. And then lastly, we will have a polynomial quiz, thinking, I guess we could do it Wednesday, but I'm pushing the can down the road. The quiz will be Friday and it will be due Sunday night. It'll be in my labs and you'll have to submit your work in Blackboard. So I know you guys don't like taking quizzes, but I've had this conversation with a few of you. The quizzes don't affect your grade all that much, so you shouldn't really stress over them. What the quizzes are for is there for you to see if you can do the problems on your own without the help functions before you have to do that on a test. It's just to help you get ready for tests, help you see what you can do on your own right now, because during the test, just like during the quizzes, you won't have those help functions. So,
I have a question.
sure enough,
How long are the tests going to be and how many questions? Because I feel like I never have enough time to finish all the questions on the quiz.
that you're asking that, if I were to look in my math lab, as in this is, I don't remember exactly how many questions there are, but if I were to look in my math lab, and I don't think I have them visible yet, but if you guys want to start doing them, I can make them visible now. They will be in the same part as the quizzes, but before each test, damn, this is slow. There's a okay, and I clicked it too many times and I'm slowing it down again. Before each test, there is a problem set, which is a practice test. And so you can go through and take this practice test as many times as you want before the test to kind of help you get ready. It's got this problem set has 16 questions on it. So I am guessing that the test itself also has 16 questions on it. Oh, no, it's got 25, so it's got a little bit more. But it's just in there to help you to practice. Okay.
Okay.
If you are having trouble with the time constraints, talk to me after class, okay?
Okay.
All right. Then, if everybody's okay, should we start picking up from where we left off? And we left off, we were multiplying polynomials. And I think the last problems that we were looking at was raising a polynomial to a power. And we had, oh, let's make this one more interesting. 2x plus 3. Let's raise it to the third power. Can anybody remember what we had to first do when we thought of raising something like that to the third power?
Would it be 8x to the third?
Nope. What we have to do before we do anything else is we have to say what we're doing is we're taking that and multiplying it by itself. 8x to the third will be part of it, but only a small part of it. We're multiplying it by itself 3 times. We cannot distribute. There is no such thing. Because there's addition in there, we're not going to be able to use our exponent rules. We've got more than one term. And so now to multiply these two, we have to, depending on what you liked last class, we have to either distribute twice or FOIL or box. I'm a FOILer, so first 2x times 2x is 4x squared. Outer 2x times 3 is 6x. Inner 3 times 2x is 6x. Last 3 times 3 is 9. And so that part becomes 4x squared plus 12x plus 9. And now we still have to multiply that by the third one, by the other 2x plus 3. And in order to do that, we said we had to distribute. We have to take the 4x squared and multiply it by the 2x plus 3. We have to take the positive 12x and multiply it by the 2x plus 3. And we have to take the positive 9 and multiply it by the 2x plus 3. Distributing here, this is where you were right. We get that 8x cubed, but then we also have to add a 12x squared. And then from here, we have to add 24x squared and a 36x. And then from here, we have to add distributing 18x plus 27. And so now when we combine our like terms, our final answer is 8x to the third plus 36x squared plus 36, 46, 54x plus 27. And that is the final answer. You know, I said, I was too quick. I apologize when you said 8x cubed. Yes, 8x cubed is a part of it, but a very small part of it. And I think that was where we left off on Friday. I think on Friday we did one together and then I gave you guys one to do on your own. Does everybody remember doing that on Friday? It's silent. Are you guys okay or not?
Yeah.
Do we need another one or no?
No,
Was that a yes or a no? I'm sorry, I didn't hear you.
no,
No, we're okay with that? And so we should be able to multiply polynomials of any size. If I had 5 terms, 5 terms, it would take a while. It would be a lot of distributing, but I should be able to multiply them. Or we should be able to raise any polynomial to any power by multiplying it by itself over and over and over again. The operation that we did not yet look at is the division of polynomials. And again, how you do it depends on the size. And sadly, in this class, we're only going to look at dividing a polynomial by a monomial. Back in the day, we used to always divide any polynomial by any polynomial, and it was a process of long division. That's very similar to doing long division with numbers. But the powers that be, that's no longer in the scope of this course. You won't be seeing that process unless you take pre-calculus. So we're going to look at dividing a polynomial by a monomial, many terms by a single term. So for example, let's start with something pretty easy. Let's start with 16x to the third minus 24x squared plus 8x. And let's put that all over 4x. And what you have to remember with these is you need to divide each term of the polynomial by the monomial. In order to do that, I like to think of taking that single fraction and dividing it into separate fractions. So I like to rewrite it as this one, 3 separate fractions. Or 1 for each term in the numerator. What the heck do I mean by that? When I look at this fraction, it's just the 16 over the 4x, it's just the 24x over the 4x, it's just the 8x over the 4x, or are they all over the 4x? The way it's written, they're all over the 4x. So I'm going to take each of those terms and divide them by that term in the denominator, divided by that 4x. And then to do each division, you have to remember to divide the coefficients. And you have to remember that you subtract exponents on a common base to divide. And so, what does that mean? Do you guys need me to wait for a minute, or is everybody in the good place to start doing the work? We okay?
Yeah.
So in this first term, 16 divided by 4 is 4. X to the third divided by x to the first is x to the second. Second term, negative 24 divided by 4 is negative 6. X to the second divided by x to the first, well, that's x to the 2 minus 1 is 1. Next, 8 divided by 4 is 2. X to the first divided by x to the first. I guess that gives us x to the 0, but x to the 0 is 1. And so we'll write that as 4x squared minus 6x plus 2 times 1 would just be 2. And so to reduce a fraction, if I have a single term in the denominator, to divide a polynomial by a monomial, a single term, we have to divide each term of that polynomial by that single term. So let's say, for example, and I have to apologize, I thought I had more examples than that out. And right now I am looking for my copy of the textbook to pull out more examples. And of course, I'm not seeing them. So I guess we'll make one up. Oh, wait, now I found it. Give me a second. What happened was when I moved the surface to get it out of the sunlight, I put it on top of the textbook. So let's look at P4 polynomials for an example. Let's do something like, oh, I actually don't have many division in here. Let's take 36x to the 5th plus 27x to the third minus 9x to the second, and divide that all by 6x to the second. And I'm going to shut up and ask you folks to please do that one for me. Did everybody take that? Because there are 3 terms in the numerator, and divide it into 3 separate division problems. Here, in the first one, 36 divided by 6 is 6. X to the 5th divided by x to the 2nd is x to the 3rd. This next one, when I look at 27 divided by 6, it doesn't go in evenly, so I'm going to just reduce that fraction and leave it as a fraction. They have a common factor of 3, so that gives me 9/2. And then subtracting exponents, it will give me x to the 1st. And last one, again, I have to reduce 9/6, which gives me 3/2. And x squared divided by x squared is x to the 0 or 1. And so that's where I would finish. How did you folks do? Everybody all right? If so, then after we go through and do all of this work with the polynomials, that next section, which is, I think, P5, deals with factoring. And if I factor a polynomial, what I want to do is I want to express it as the product of prime polynomials. Well, what does it mean for something to be prime? We say that a number is prime. We say we have a prime number if its only factors are 1 in itself. Oh Lord, how do you spell itself? Definitely not like that. Yeah, that looks better. Otherwise, we have a composite number. Which is one that can be expressed as the product of primes. And while we're on this list, we're going to say that 1 is neither prime nor composite. It's considered the basic unit. So, for example, if I have something like, let's say 24. Would 24 be prime or composite? Is everybody all right? 24 would be a composite number. If I look at the number 24, and some of you might have seen that idea in the past of a factor tree. Can anybody think of two numbers that multiply to give me 24?
6 and 4.
I heard a couple, what I heard loudest was the 6 and 4. Can you think of two numbers that multiply to give me 6? 2 and 3. And 4 is 2 times 2. And so we'd say that the prime factorization of 24 is 2 times 2 times 2 times 3, or 2 to the third times 3. And we've expressed it as a product of primes. Instead, if I have a number like 13, is there anything that goes into 13 evenly?
No.
No. So 13 is a prime number. And so what we're going to be trying to do is we're going to be trying to factor not numbers, but polynomials. And in order to factor polynomials, there's different type of factoring that we do. And the first type of factoring that we look at is the greatest common factor which is sometimes abbreviated GCF. To find the greatest common factor of terms, we first look for the greatest common factor of the coefficients. And then we use the lowest exponent on common variables. So what's that all about? Let's say, for example, I ask you to find the greatest common factor of, let's say, 6x to the fourth, 18x to the third, and 12x squared. So what's the largest number that divides? What's the largest divisor of 6, 18, and 12? What would be the largest number that goes into all three of those evenly? Well, I think we can get bigger than 3.
6.
6. Aren't they all divisible by 6? And then they all have a common variable, which is x. And the lowest exponent on x is 2. So the greatest common factor, putting those pieces together, would be 6x squared. And we're going to use that to factor the greatest common factor out of a polynomial. The first thing that we're going to do is we're going to find the greatest common factor of all the terms. Then we're going to divide the polynomial by their greatest common factor. And then we're going to express the polynomial as the product of the greatest common factor and the quotient. And so if my directions asked me to factor 6x to the 4th minus 18x to the 3rd plus 12x squared, we just found the greatest common factor of those terms to be 6x squared. And so when I divide that by 6x squared, and again in my head, I'm thinking of taking each of those terms and dividing them by 6x squared. I end up with 1x squared minus 3x plus 2. And so common factoring, I'd say that 6x to the 4th minus 18x to the 3rd plus 12x to the 2nd is equal to 6x squared times x squared minus 3x plus 2. And we could check by multiplication. And so if I were to multiply 6x squared times x squared, 6x squared times minus 3, 6x squared times positive 2, it should give me that same polynomial back. This, though, would be my factored form. And again, this is only using the greatest common factor. And it gets me to this idea of factoring is kind of like, I think of it as math Jeopardy. Has anybody ever seen that television show Jeopardy, where they give you the answers and you have to say what the question was? And so this is the answer to a multiplication problem. What was I multiplying? I'm working backwards. I'm undoing the multiplication. And whenever you see the directions factor, the first thing that you should do is look for a common factor. So whenever you factor, you have to first find if there's a greatest common factor. So let's look at a couple of examples, starting with easier ones and working our way up. Before I do that, does anybody have any questions? So for each of these, the directions are to just factor out the greatest common factor. First one, I'm going to look at 16x minus 24. Can anybody think of the largest number that divides both 16 and 24 evenly?
8.
8. And they both don't have the same variable. So what I'm going to do now is I'm going to take that and divide by 8, which has the effect of dividing each term by 8. And that leaves me with 2x minus 3. And so my factored form is 8 times 2x minus 3. That's what we're saying our answer is. But I always like to do a check. When I distribute, I get 16x minus 24, which is what I started with, so it checks. So far, so good. Next example, let's look at 9x to the 4th minus 18x to the 3rd plus 27x squared. And I'm going to shut up and ask you folks to please do this one for me. Can we go over yet, or do you guys need more time?
One more minute.
Okie dokie. Ready?
Yeah.
Did everybody get the common factor to be 9x squared? And if I divide by 9x squared, I get x squared minus 2x plus 3. So my final answer would be 9x squared times x squared minus 2x plus 3. Do we need to add details, or is that all right? You okay?
Yeah, that's fine.
So the next example is a little bit different. And because this one's different, I guess we'll start by going over it together. What if I have x times x plus 5 plus 3 times x plus 5? Does everybody see this one? The common factor is a binomial. So we're going to say that the common factor can be a polynomial. And so what they have in common, both sides of that plus sign, is a factor of x plus 5. And usually I don't take the time to write this. But if I divided them both by the x plus 5, I'm left with x plus 3. And so my factor form will be the x plus 3 times the x plus 5. Can everybody wrap their minds around that? So next example, let's factor. Right now, using just the greatest common factor from, let's take x squared times 2x plus 5 plus 17 times 2x plus 5. What do they have in common?
2x plus 5.
Beautiful. Is it obvious if I divided out the 2x plus 5, what I'd be left with is x squared plus 17.
Yep.
And so this would be my factored form. And that takes us to what will be the next type of factoring we're looking at, which will be factoring by grouping. And to factor by grouping, I'm going to use, usually, if my polynomial has 4 terms. There are some 4-term polynomials that will not factor by grouping. And we'll look at those later to factor in another way. But usually, if I'm going to use factoring by grouping, I'm applying it if I have 4 terms. So let's look at example. let's look at x to the third minus 2x squared plus 5x minus 10. Again, whenever I factor, the first thing I ask is there a common factor to all terms? And with this one, the answer is no. Then, if there are 4 terms, I start by dividing it into, not divide, let's say split, into 2 binomials. Just split it in half. Draw a line down the middle. Then what I'm going to do is common factor each binomial. So let's look at just the front part. Just the front part. X to the third minus 2x squared. What would the common factor be?
X,
Yep, and what's the lowest exponent on those x's?
2.
So my common factor is x squared. And so now to find the other factor, I'm going to think of dividing out the x squared. And that's going to give me x minus 2. Is everybody all right there? Then I'm going to look at the other binomial, the 5 plus 5x minus 10. Is there anything common there? 5. What type of 5? Positive or negative? Use the middle sign. I'm going to take out a positive 5. And when I divide out that 5, what am I left with? 5x divided by 5 is x. Minus 10 divided by 5 is minus 2. So far, so good. Now, hopefully, if we did everything right, the 2 binomials have a common binomial factor. Does everybody see how both halves have a factor of x minus 2? And when I divide that out, I'll be left with x squared plus 5. And so this is my final answer.
Where are we getting the x squared plus 5 from? Never mind.
Do you see it now?
Yep.
What we're doing is we're taking the common factor is x minus 2, and so we're thinking of dividing the x minus 2's out. But I have to apologize. I get to this place where I'm kind of like a little kid. I say that maturity is the function of height. Those of you who've seen me already know I'm not a very tall person. So I act like a little kid too much. I say, okay, the x minus 2 is common. When I divide it out, it's almost like crossing it out and saying what's left over. And what's left over would be that x squared plus 5. Technically, we're dividing out the common factor, but in all practicality, we're saying if I take that common factor away, what's left? Does that help?
Yep.
So let's look at another example. Let's look at three x cubed minus 2x squared minus 6x plus 4. And is there an overall greatest common factor to all the terms? Anything that divides all 4 terms? No. So then I always ask myself, how many terms? And when it's 4, I go to my grouping. To do my grouping, I'm going to split this in half. And so now I took that one factoring problem, one big bad factoring problem, and turned it into 2 smaller factoring problems. First 2, what do they have in common?
X.
What's the lowest exponent on that x?
2.
So we'll take out x squared. And when I divide that, so that's my common factor. When I divide that from both, we have 3x minus 2. Is everybody comfortable with that? Then in the back, what's common between both of those?
2.
2. Now over here, I always use that sign. So I'm going to take out a -2 because that's a minus sign out front. Now, if I divide minus 6x by minus 2, I get positive 3x. And if I divide positive 4 times by -2, I get -2. Now, I look back at my handiwork and I keep my fingers and toes crossed, because if life is good, the binomials match. Do they?
Yep.
So one factor is 3x minus 2, and the other factor would be x squared minus 2. And you see that if I use the repeated distribution, it would take me back to where I started from. So let's do one more of these. Let's look at x cubed minus x squared minus 5x plus 5. And I'm going to shut up and ask you folks to please factor this one for me. How you guys doing? Do you need more time? Or do you have it?
Yeah, I'm gonna.
I'm sorry, I heard you say something, but I couldn't make out what you said.
Yeah, I've gotten it. I've got it.
You got it?
Yeah.
Did anybody else get x squared minus 5 times x minus 1?
No.
Okay, let's look at it then and add the details.
I got it in the reverse.
Oh, that's fine. Now I'm going to be tricky. What says that if I'm multiplying, I can flip flop and change order?
Okay,
It's the commutative property. So you're fine if you reversed them. But if you didn't get anywhere near, let's say, see, there's 4 terms, nothing in common. What do these first two have in common? They both have x's. The lowest exponent is 2. And when I divide them by x squared, x cubed divided by x squared is x. Minus x squared divided by x squared is minus 1. To that point, is it better?
Yep, that's the part I left out.
And then both of these guys have a 5. And I always pull that leading sign. So I'm going to take out a negative 5. Minus 5x divided by minus 5 is positive x. Positive 5 divided by negative 5, positive divided by negative would be negative 1. Some of you might have taken out a positive 5 instead. And if you took a positive 5 out instead, your signs didn't match. And so you didn't have matchy. If that's what happens, if these guys don't match, try changing that sign. But now, because those guys do match, that's my common factor. And when I divide that out, I'm left with the x squared minus 5.